Welcome to the lesson on surface areas and volumes of combinations of solids. At the end of this lesson, you will be able to calculate the surface area and volume of a cube, cuboid, sphere, hemisphere, cylinder and a cone. Additionally, you will be able to calculate the total surface area and volume of a solid composed of a combination of fundamental solid shapes. The solid shapes that we have encountered so far in mathematics are simple fundamental shapes like cubes, cuboids, spheres, cylinders or cones. You have also learned how to solve problems that are related to surface areas and volumes of these shapes using standard formulae. Let us revisit the standard formulae for calculating areas and volumes of fundamental solid shapes. The curved surface area, or CSA, is the area of the curved surfaces for the solid. The remaining surfaces of the solid are the flat or the non-curved surfaces. In a cone, the flat surface is the circular area of the base. In a cylinder, the flat surfaces are the top and bottom circular areas. A sphere has no flat surface, whereas a cuboid and a cube have only flat surfaces. The flat surface area and the CSA of a solid together add up to the total surface area, TSA, for the solid. Take a moment to review all the formulae. You must remember the formulae in order to solve problems on areas and volumes of solids. In real life, you will encounter a variety of complex shapes which are made up of a combination of simple solids. When you try and solve problems on surface areas and volumes for complex shapes, you run up against difficulty. You cannot directly apply the standard formulae to these complex shapes. There is, of course, a fairly simple approach that is used for calculating areas and volumes. The trick lies in recognizing the fundamental solid shapes which make up the complex shape. A simple approach used for calculating the surface area and volume for complex shapes is: split up the complex solid shapes into fundamental solid shapes. Apply a standard formulae to the fundamental shapes to calculate areas or volumes and add the results of the calculation. This brings us to the end of this section. Hope you enjoyed your learning experience. Welcome to the lesson on the conversion of solids from one shape to another. At the end of this lesson, you will be able to set up an appropriate equation which will lead to a solution for problems on the conversion of solids. You will also apply your knowledge to solve selected problems. When we cut a watermelon into slices, we are converting a solid shape into other solid shapes. Regardless of the size and shape of the slices, there is one fact that holds true of the whole process. The volume of all the slices together exactly equals the volume of the original watermelon. When we convert a solid of a given shape to a solid of another shape, the surface area usually changes. However, the volume is preserved. This is the basic principle that is at the heart of any problem in the conversion of solids from one shape to another. The volume of material that we start with and the volume that we end with remain the same. In many cases, a single solid item is converted to a number of items, and we are asked to compute the number of such items that can be produced. In other cases, we are given the available number of items of a converted solid. We are asked to compute the height, radius, or some other dimension of the converted solid. Whenever a solid shape is converted to another shape, the volume of the object on the left always equals the total volume of the objects on the right. This equality can be expressed as the equation volume of one object equals n into volume of each shape of the second object. The quantity n is the number of objects on the right. In some problems that we will be asked to solve, we will be provided with the shape and dimensions of both objects. We will be asked to determine the value of n. For the example on the screen, we convert a cuboid of dimensions 6 into 2 into 2 centimeters to a number of cubes of side 2 centimeters. We are asked to find n, which is the number of cubes produced. We will equate the volumes to get 6 into 2 into 2 equals n into 2 cubed. We will then solve for n to get n equals 3. In some problems, n is provided, but the dimension of the object may not be. We have to determine the value of the missing dimension. For the example on the screen, we convert 8 into 2 into 2 centimeter cuboid to 4 equal cubes. We are asked to find L, which is the length of the side of the cubes produced. We will equate the volumes to get 8 into 2 into 2 equals 4 into L cubed. We will then solve for L to get L equals 2. Yet another type of problem that we may be asked to solve is if the shape of an object is changed. We have to determine the resulting surface area. For the example on the screen, we convert 3 equal cubes of side 2 centimeters to a 6 into 2 into 2 centimeter cuboid. We are asked to find the total surface area of the cuboid. When a solid changes shape, even though the volume remains the same, the change in geometry of the shape causes the surface area to change. We will use the standard formula to calculate the surface area for the resulting cuboid, which works out to 56 square centimeters. It is interesting to compare the areas for the initial and final shapes. The surface area for the 3 cubes is equal to 3 into 6 into L square, where L is the length of the side of a cube. This evaluates to 72 square centimeters. We have evaluated the surface area of the cuboid to be 56 square centimeters. As is evident, the areas are not equal. Welcome to the lesson on the frustum of a cone. At the end of this lesson, you will be able to define the frustum of a right circular cone. You will also be able to determine the surface area of the frustum of a cone. Additionally, you will be able to determine the volume of the frustum of a cone. Buck Zach is an enthusiastic gardener. He has just bought additional flower pots for his garden and is planning to buy some paint for the new pots. He is also planning to buy some soil to fill the pots. As Buck Zach leaves for his shopping, he realizes that he does not have the slightest idea how much paint he requires or how much soil he should buy. Actually, Buck Zach needs to buy enough paint to cover up the curved surface area of all the flower pots. The amount of soil he needs to buy equals the volume of all the flower pots. The flower pots that Buck Zach has bought have a shape called the frustum of a cone. A frustum of a cone is created by slicing off the top of a cone. As a definition, we may say that when we cut a right circular cone with the plane parallel to the base of the cone, then the solid shape between the plane and the base of the cone is called the frustum of a cone. The surface area and the volume of the frustum of a cone can be calculated using standard formulae. The CSA of the frustum of a cone equals pi into L into R1 plus R2, where R1 and R2 are the radii of the larger and smaller circular faces of the frustum respectively. L is the slant height of the frustum. The slant height can also be expressed as root h square plus R1 minus R2 the whole square, where R1 and R2 are the radii of the circular faces, and h is the height of the frustum of the cone. Using the expression for L, the CSA of the frustum can also be expressed as pi times R1 plus R2 into under root h square plus R1 minus R2 the whole square. The formula for total surface area TSA for the frustum of a cone is pi times L times R1 plus R2 plus pi times R1 square plus pi R2 square. As before, the slant height L equals under root h square plus R1 minus R2 the whole square. The formula for volume of the frustum of a cone is 1 upon 3 times pi h times R1 square plus R2 square plus R1 R2, where R1 and R2 are the radii of the larger and the smaller circular faces of the frustum respectively, and h is the height of the frustum.